Hello, everyone, and again, also welcome to this seminar, also from my side. So just to, as Kasia said, our working group focuses on quantum field theoretic and QFT aspects of quantum information. Just to give you a very broad overview of the things that, well, there are many topics that fit into this working group. On one hand, there's been a lot of progress on the side of looking at, measurements and other operational aspects in QFT and QFT-based approaches. And on the other hand, there's been a lot of recent progress on information theoretic approaches to studying the interface of quantum theory and relativity. And in particular, which try to focus on relativistic principles like no superluminal signaling and their implications for quantum information tasks in spacetime. So in that context, I'm really glad and very happy to welcome our first speaker of the seminar series, Emily Adlam. She's currently an assistant professor based at Chapman University, I guess the Institute of Quantum Studies and Department of Philosophy. And she previously did her PhD at University of Cambridge, working on relativistic quantum tasks. And I should say, apart from very interesting work on this relativistic quantum tasks, I think Emily has worked on most of the important questions and foundations from causality, time, relationalism, and the measurement problem. So we're very happy to have her as our first speaker for the seminar series. And without further ado, I'm happy to welcome Emily, and please, you can get started whenever you're ready.
Great. Thank you very much. It's lovely to be here virtually with you. And yeah, I was very excited to have a chance to speak about some of this work that I did during my PhD with my supervisor, Adrian Kent. So I'm going to start by talking about summoning in general and the sort of idea of summoning and why the no summoning theorem was important and interesting. I'll then talk about two major generalizations of the summoning task, one due to Hayden and May and another one due to Adrian and myself. And so I'll talk about what is different about those tasks and what we can learn from the theorems characterizing them. Finally, I'll sum up by talking about what exactly we learn from this, and in particular, how quantum are these phenomena really. So the quantum no summoning theorem was proposed by Adrian back in 2013. And it was interesting at this time because it was, to my knowledge, the sort of first major example of a quantum information task, which also was strongly based on relativistic principles. So it was a really interesting demonstration of the ways in which quantum mechanics and relativity interface and constrain the possibilities for processing information. So the basic setup of summoning goes like this. We have our two agents, Bob and Alice. So Bob is going to give Alice a quantum state at a fixed space-time point, which I'll call the start point. So Bob knows what state he has given Alice, but Alice does not know what the state is. So for her, this is an unknown quantum state. So the idea is that at some later point, some point in the future, like kind of the start point, Bob is going to request that quantum state back from Alice, and Alice's job is to produce it immediately. So to make Alice's life easier here, we're going to allow that Alice is allowed to have an unlimited number of cooperating agents spread throughout space-time to sort of implement her needs in order to return that state to Bob. But it turns out that even if we give Alice unlimited resources in that sense, in general, Alice will not be able to guarantee a successful response to Bob, regardless of when and where he asked for that state. So the reasons for that follows from the combination of the no signaling theorem from relativity plus the no cloning theorem from quantum mechanics. So to see that, let's imagine for the purpose of obtaining a contradiction that Alice can guarantee a successful response at any point where Bob might make a call. So then we can imagine some run of this task on which Bob, perhaps by mistake, makes two calls at two space-like separated points. Now, from the no signaling theorem, we know that the occurrence of a call at one point cannot prevent the successful response at the other space-like separated point. So given that Alice has a protocol which guarantees a successful response whenever Bob makes one call, it must be the case that when he makes these two calls, she ends up returning the state at both of these space-like separated points. But if she does that, that means she's cloned the state. So she's taken an unknown quantum state and produced two copies of it. that of course would be a violation of the no cloning theorem. So what that tells us is that it must not, in fact, be possible for Alice to guarantee a successful response at any point. If she could do that, she would either be violating the no cloning theorem or she would be violating the no signaling theorem. So this is a very simple task, right? Nothing very complicated is going on here, but it does combine principles from quantum mechanics and from relativity in non-trivial ways and leads to a sort of unique result about how we can process information in space-time. So in addition to being foundationally interesting, you can sort of see that this kind of summoning task potentially has important applications in the context of things like distributed quantum computing. So for example, you can imagine a distributed computation where several sub-protocols are running in parallel, which might require that the output of some sub-protocol will be routed to one of several parallel computations, which are going to call for the output when they reach a certain state. You can see that in a sort of relativistic context, the possibilities for doing that and the speed with which you could implement such a computation is going to depend on your ability to summon states at various different points in space-time to put them into these sub-protocols. So understanding summoning tasks can help characterize what distributed computation is possible and the extent to which we can complete these kinds of computations. More specifically, the teleportation model of distributed quantum computing, in which we apply gates to quantum states by teleporting them, is in effect a summoning task. Each round involves a situation in which we measuring a system to teleport it and then performing some transformation on it depending on the result of that measurement. So we essentially need to be able to summon it to various different places in order to perform the appropriate transformation to restore the state that we wanted. So that is, in effect, a summoning task, particularly if these things are happening far apart from each other in a distributed scenario. It's going to be important to understand what are the possibilities for distributing quantum states in that way. So both for the sort of foundational interest of the thing and also for these sort of practical applications, it's going to be helpful to move beyond the original no summoning theorem and consider which summoning tasks are possible and which summoning tasks are not possible. So that's what Hayden and May set out to do with their generalization of the summoning theorem. So now, rather than allowing Bob to call for the state anywhere in the future light cone of the start point, we're instead going to have a more restricted task where we have some fixed number of possible call points. We say that Bob is definitely going to ask for the state at exactly one of these call points. Then with every call point, we associate a corresponding response point in its causal future. And we say that Alice is supposed to return the state at the response point corresponding to the call point. So Alice has responded successfully if she gives the state back at the right response point. If she doesn't manage to do that, then she has failed the task. And so we're going to be interested in the circumstances in which Alice can guarantee a successful response to this task. So some distributions of call response points, it's possible for Alice to guarantee a successful response. Other distributions, there's no way she can guarantee a successful response, although she might accidentally succeed in some cases. So Hayden and May set out to prove necessary and sufficient conditions characterizing which tasks Alice can guarantee a successful response to. So under the assumptions I've just described, it turns out that it's possible to guarantee a successful response if and only if the following conditions are met. The first is just that every reveal point must be in the future light cone of the start point. That's pretty obvious. No signaling clearly indicates that Alice isn't going to be able to send the state to a point that's not in the future light cone of the point where she receives it. But the other condition is slightly more complex. It says that for any pair of call points, the corresponding causal diamonds are causally related. So there has to be a time-like or a light-like curve passing from one causal diamond to the other. So the term causal diamond here just refers to the region of space-time which is in the future light cone of the call point and the past light cone of the corresponding response point. So the causal diamond is the region of space-time in which Alice and her agents know that a call has been made and still have time to try to make a response. So that's kind of the active region in which they will be trying to respond to that call. So this theorem provides a complete characterization of the tasks which can and can't be completed. And so what is particularly interesting about this theorem is that although it is true that Alice can't respond to any summoning task, that's what the no summoning theorem says, it does turn out that she can do better than you might naively imagine she could. So in particular, if you're sort of thinking about summoning on the analog of something like a sort of classical object that you can't duplicate, you might think, well, Alice is only going to be able to respond successfully if there's a continuous path beginning at the start point, which runs sequentially through all the causal diamonds. In that case, of course, she'll just send her classical object through the causal diamonds and she'll give it back to Bob when she hears his eventual call. But it turns out that's not necessary in the quantum context. So there are distributions which satisfy the conditions described here, but which don't have a continuous path running through all of the causal diamonds. So to satisfy those tasks, Alice is going to have to do something more complicated, involving distributing information, quantum information over space-time, and then putting it back together in the right way to respond to the task. So I'll just give a sort of high-level summary of what the proof of this theorem looks like to give a sense of why it is true. So first, the proof of the necessity of the second condition. That this necessity proof is pretty similar to the one in the original no summoning theorem. It kind of comes directly from no cloning and no signaling. So if it were possible to guarantee a successful response to a task violating the condition, a task in which we have two causal diamonds which are not causally related to each other, then clearly if we run that task and Bob, perhaps by accident, makes calls in both of those causal diamonds, then because they're not causally related, the call being made at one causal diamond can't influence what response Alice makes in the other one, and vice versa. So if Bob makes these two calls, and Alice would have responded successfully if he had made only one call, she must respond successfully in both diamonds, even when he's made two calls, so she's going to return two copies of the state. So again, we have done cloning. So that shows that the conditions set out in the previous slide are necessary. Alice isn't going to be able to guarantee a successful response if they're not met. But we can also show that they are sufficient. So as long as these conditions are met, Alice can guarantee a successful response to the task. So to show that to be the case, we need to construct a protocol that Alice can use to guarantee a successful response to any task meeting these conditions. And to do that, we're going to use a recursive protocol based on a cryptographic procedure known as quantum secret sharing. So quantum secret sharing involves a situation in which we take an unknown quantum state and we divide it into shares. So specifically, we're going to divide it into n shares such that any k of these shares can be used to reconstruct the state, but any set of k minus 1 or fewer shares contains no information about the state. So this is known as a kn secret sharing scheme. And you can see that clearly k must be greater than half of n, because if k were half n or less, then you could use half of the shares to reconstruct one copy of the state and the other half to reconstruct another copy, and thus you would have cloned the state. That's not allowed, so k has got to be greater than half of n. But perhaps surprisingly, it turns out that for any k that is greater than half of n, it's always possible to construct an appropriate quantum secret sharing scheme. So even if you have only just more than half of the shares, you will still be able to reconstruct the whole state. That might seem a little bit surprising. You might think you should have lost some information because of all the shares you don't have, but because of the way the state is encoded, it turns out as long as you have more than half, you can reconstruct it. So using secret sharing, we can construct a recursive protocol that will always succeed in this task as follows. So because it's recursive, I'm going to start with the base case with 2 pairs and then show how to construct a protocol for more than 2 pairs. So if we've just got 2 causal diamonds, we know that they must be light-like or time-like related to each other. So one of those response points is going to be in the future light cone of the other call point. So what we'll do is we will set up our scenario such that there's an entangled pair shared between the start point and the first call point. So when Alice receives the state at the call point, she's going to perform a measurement which teleports that state to the first call point, and at the same time, she also sends the classical teleportation data directly to both response points. Now, if a call is received at the first call point, Alice's agent there can just forward the state on to the first response point, and then we can reconstruct the original state using the classical teleportation data. If a call is not received at the first call point, Alice will just send the quantum state directly to the second call point, the second response point, because she knows that must be the one where the call is made. Again, the classical teleportation data will be there so she can reconstruct the state. So in the 2-pair case, she can do this protocol and she will always succeed in responding to the call. So for n pairs, what we're going to do is we will use an n-1 threshold secret sharing scheme to make shares of the unknown state. So then we can look at our n pairs and we can identify n subsets of those pairs of size n-1. So we're going to give one of our shares to each of those subsets. What we're then going to do is take each subset and break it down again. So we'll make another secret sharing scheme, sharing the share that we have received using an n-2, n-1 secret sharing scheme, and again distribute across all subsets. And we keep going all the way down until we get down to our base case with 2 pairs where we know how to successfully respond. So putting that all back together, what will happen is that when a call is made at some call point, with all of this, recursion is going to ensure that enough shares of the state are returned at the corresponding response point that Alice's agents can always reconstruct the full state and give it back to Bob. So you can see using this recursive protocol that any scenario which obeys the conditions set out earlier is going to be able to be responded to successfully by Alice. Now, of course, in a practical situation, particularly if n is large, this is going to be an incredibly inefficient way of responding to the task. It's going to involve creating a very large number of shares of the quantum state and doing a lot of recursion. So in many situations, there would be a more efficient protocol which you could use than this one. And indeed, Hayden and May do set out some suggestions for more efficient protocols. But the point of this one is just to show that, in principle, it is always possible to respond to a task like this. So the conditions set out are both necessary and sufficient. Great. So Hayden and May have given us some very useful information about the ways in which quantum states can, in principle, be distributed over spacetime. But you might wonder to what extent the features of the result there are sort of consequences of foundational features of quantum information in spacetime versus which are sort of features of the specific setup. So to explore that question, Adrian and I looked at a different generalization of the summoning task and aimed to sort of compare the task that can be completed in the original version and as compared to our other generalization. So to motivate what's interesting about our generalization, we have this story about a magician. So imagine that you meet a magician who wants to do a magic trick for you, and the magic trick requires that you give him an item that you are very confident he can't quickly duplicate. So he takes this object that he can't duplicate, he goes behind a curtain and puts it in one of n boxes. Then he opens the curtain, he lets you choose a box, and then he opens the box, and lo and behold, it turns out that your item is inside. So a pretty cool trick. He managed to sort of summon the item to whichever box you chose, despite not knowing which one you were going to choose in advance. So being a curious person, you decide to have a bit of an experiment, and so you suggest repeating the task. So again, he goes behind the curtain, does what he does again, and then he opens the curtain again and lets you choose. But this time you choose 2 boxes and you allow him to choose which one to open. So I guess naturally we might imagine that if he could do it when you specify just 1 box, he surely must be able to do it if you specify 2 boxes because you're giving him more choices about how to respond. That ought to make his life easier. But it transpires that this time he can't do it. So something weird you might think is going on here. Intuitively, you should have made his task easier, but somehow you made it harder. So with that in mind, we're going to go on and look at another summoning task, which seems to show this kind of behavior. So the generalization is a pretty simple generalization. It's just, let's imagine allowing multiple calls rather than just 1 call. So the Hayden and May setup assumed as part of its definition of the task that Bob is only going to make 1 call. So the question you might have at this point is, what if Bob does make more than 1 call? So of course, we can't require that Alice returns the state at more than 1 response point, because if she could do that, she would have cloned it. So we need to define this task such that Bob is allowed to make more than 1 call, but in order to respond successfully, Alice just needs to respond to any one of those calls. So it will allow her to choose to respond to whichever one she wants. She just has to respond to 1. So kind of as in the magician task, you might naively think that if Bob is going to make multiple calls and allow Alice to respond at any of those points, that surely could only make Alice's life easier. He's giving her more options. Should be easier for her to get the state to at least one of those places. But it turns out that, in fact, having this unrestricted calls will actually make the task harder rather than easier. So we can see that from this theorem here, describing the necessary and sufficient conditions for the unrestricted task. So as in the previous case, we look at the tasks for which Alice can guarantee a successful response. And it turns out she can guarantee that if and only if the following conditions are met. So first, we need that every reveal point is in the future light cone of the start point, just for the same reasons as in the previous case. And then the second condition, though, is different. It says that for any possible subset K of the call points, there is at least one member of the subset for which the corresponding response point is in the future light cone of all of the call points in the set. So I'll compare that to the previous task in a minute, but let's first look at how the proof works. So again, the first condition is pretty trivial, so I'll focus on the second one. To prove the necessity of the second one, first note that we can safely assume that Alice is using a deterministic protocol. So by deterministic, I mean that for every possible subset of the call points, there is one specific response point that Alice will respond at if Bob makes calls at those points. So we can sort of write down a map which takes a subset of the call points to the one call point at which Alice will respond if Bob makes calls at those points. So that's the sense in which it's deterministic. We can assume that because probabilistic protocols are always going to be convex sums of deterministic ones. So if Alice can't guarantee success with a deterministic protocol, then she isn't going to be able to do that with a probabilistic protocol either. So with that in mind, let's suppose, for the purpose of obtaining a contradiction, that there does exist a successful deterministic protocol for some summoning task with M call response pairs, which has the property that for every call response pair CI-RI, there exists at least one other call response pair CJ-RJ, such that the response point of the first pair is not in the future light cone of the second pair. So that's just saying that the condition I've described previously is not met. We have a violation of that condition. So let's suppose that the condition is violated, but nonetheless, there exists a successful deterministic protocol. Now we can see that from no signaling, the response that is made at the point Ri when calls are made at some set of call points Q, which includes the point Cj, where Ri is not in the future light cone of Cj, the response there must be the same as the response made at Ri when calls are made at the set Q, not including Cj, because of course we can't know at Ri whether a call has been made at Cj or not, so the response is going to have to be the same either way. So what that tells us is that the sets for which a response is made at Ri must come in pairs. For every such set, including Cj, there must be a corresponding set not including Cj. So that means that for any of our response points, if Qi is the total number of subsets such that the state is returned at Ri if calls are made at all points in that subset, then Qi must be even because the members of Qi have to come in pairs. Clearly then, if we sum Qi over all of the response points, we can see that the total sum over all of that must be even, since it's the sum of even numbers. But we can also note that in order to guarantee a successful response, we know that Alice must respond at exactly one point whenever calls are made at any subset. So that means that the sum over all I of the Qi's must be equal to the total number of possible subsets at which Bob could make calls. And that number is given by 2 to the power of m minus 1. And that, of course, is an odd number. So we have obtained a contradiction, right? We have shown that this number is both even and odd. That's impossible. We can conclude, therefore, that there cannot exist a successful deterministic protocol for a task with this property. So that proves most of the condition that I set out previously. The final observation to make is that this argument will hold for any subset of the points in a larger summoning task. So that tells us that the condition I've described must hold not only for all of the points together, but also for any subset of them. So that shows that that condition is indeed necessary. To show that it is sufficient, as before, we're just going to come up with a protocol that Alice can use to guarantee a successful response to any task which satisfies this condition. So to do that, first note that if we have a task with n pairs which does satisfy this condition, then there must be at least one response point which is in the future light cone of all the call points. So we can relabel that pair with the number n, the largest number. We can then look at the subset excluding that pair. Because every subset is also required to obey the condition, that tells us there is going to be one response point in the future locale of all of the call points in this subset. So again, we can kind of relabel things. We can just relabel this pair as n-1, so the second largest number. And we can just keep going all the way down, relabeling all of the points until we have reordered the pairs in such a way that for any subset, the last pair in terms of the numbering has its response point in the future light cone of all the prior call points. So having done that, we can then set up the following protocol. So first off, let D be the dimension of the Hilbert space of the unknown state that Bob is going to give to Alice. We'll allow that Alice is allowed to know the dimension. Then before the protocol begins, Alice is going to share entangled pairs in the Hilbert space shown here between various pairs of agents. So in particular, she's going to share one pair between the start point and the first call point. She'll share another pair between the first call point and the second call point. She'll share another pair between the second call point and the third point, and so on and so forth, all the way up to the last call point. So she's got a sort of sequence of entangled pairs connecting all of the different causal diamonds and the start point. So with that done, we can then start the protocol, and what Alice is going to do is this. At the start of the protocol, she will perform a teleportation measurement which teleports the state to C1, and then she will just broadcast her classical teleportation data in all directions such that it will be available anywhere in the future light cone of the start point. So the agent at the call point C1 will wait to see if a call occurs. If a call does occur at C1, they will just send that received state on to the corresponding response point. Because that response point is in the future light cone of the start point, the classical teleportation data will be at that response point, and so the state can be reconstructed at the response point and handed back to Bob. Meanwhile, if no call occurs at C1, then we can perform the teleportation measurement once again and send the transformed state onto C2. And again, we're going to broadcast all the classical data so that it is available everywhere in the future light cone of C1. So now if a call occurs at C2, we'll send the received state to R2. R2 now is in the future light cone of both the start point and C1, so the classical data from both teleportations will be at R2, so the state can be reconstructed. If no call at C2, send on to C3, and so on and so forth. It's just a sort of sequence. So eventually a call will be made, the transformed state will be sent to a response point, some amount of transformations will be done conditioned on the received classical teleportation data, and so Alice will always succeed in giving Bob back the original state. So that shows that the conditions set out on earlier are not only necessary but also sufficient. Alice can always guarantee success if those conditions are met. Okay, so with that in mind, we can make a comparison of these two different summoning tasks. And what we see pretty straightforwardly is that summoning with unrestricted calls is harder. That is, every arrangement that satisfies the unrestricted theorem, where we have any number of calls allowed, is also going to satisfy the restricted theorem due to Hayden and May. But the converse is not true. There are arrangements which satisfy the restricted theorem due to Hayden and May, but which do not satisfy the unrestricted theorem where we allow multiple calls. So the diagram here shows one such arrangement. So the red lines and black lines here are both going to represent either time-like or light-like connections. So what we can see here is that C3 there's an arrow going from C3 to the response point for C2. So the causal diamond for C3 is causally related to the causal diamond for C2. There's also a red line going from C1 to the response point R3. So that tells us the causal diamond for C1 is causally related to the causal diamond for C3. So C3 is causally related to both C1 and C2, and we can go around and see that's true for all of them. Each causal diamond is causally related to all of the other causal diamonds. So those were the conditions for the Hayden and May theorem. So this arrangement satisfies the Hayden and May theorem, and so this arrangement, Alice can guarantee a successful response if she knows there will be only one call. But you can also see that this arrangement is not going to satisfy the unrestricted theorem. It's not going to satisfy it because if you look at these three response points, there is no single response point which is in the future light cone of all three of those call points. So the condition set out in the unrestricted case is not met. And so Alice will not be able to guarantee a successful response to this task if Bob is allowed to make more than one call. So as we sort of motivated earlier, you might initially think that is a bit strange. How is it that giving Alice more freedom about how to complete the task makes it more difficult for her to complete the task? So the key point here is that this new task is kind of giving us insight into the role that is being played by the one call limitation in the original Hayden-May task. The way it was sort of set out in the original Hayden-May paper, it sort of seems that the one call limitation isn't doing anything too important. It's really just there to ensure that Alice isn't required to return 2 copies, because of course it would be impossible for her to return 2 copies. So it sort of seems from that point of view as though the one call limitation is just kind of a trivial point that is needed to make that possible. But the one call limitation is actually doing much more than that. Specifically, what the one call limitation does is that it gives Alice quite a lot of information about what is going on elsewhere in spacetime. So if Alice is in the restricted case where she's promised that only one call is going to be made, what that means is when she learns that a call has been made at a point, she knows for sure that no call will be made at any other call point, and so she can use that information to coordinate the behavior of her agents across space-time. She can use it to help them decide where they should send their shares of the quantum state in order to make sure that we get enough shares arriving at the response point where the call has been made. And so that information actually is very useful in coordinating that kind of bringing the shares together and reconstructing the state. On the other hand, in the unrestricted case, when she sees a call at some call point, that tells her nothing at all about what's happening at the other call points. So she has less information about what's going on in other parts of space-time, and that makes it harder for her to coordinate her agents. They're not going to be able to coordinate to make sure they all get the shares of the state to the same place, because they won't necessarily know if they've seen a call. Is my call the only call, or are there calls elsewhere? What are the people in other causal diamonds going to be? There's no way to sort of coordinate them to make sure that they all converge on sending their shares to the same response point. So what we see here is that at least some features of the result we saw in the original Hayden-May case were in some sense perhaps not intrinsically quantum relativistic features, but were partly to do with the way the task had been defined. So by comparing these two tasks, we can get a better sense of what is sort of really quantum and relativistic here versus what is more just a feature of the definition of the task. Okay, so one natural question you might have at this point is about how relativistic and quantum these no-summoning results really are. I think it's clear that they are very relativistic because they do depend very heavily on the sort of relativistic light cone structure of space-time and the impossibility of superluminal signaling. So sort of no doubt that relativity is playing an important role. But you might perhaps think that it doesn't seem like quantum mechanics is playing that big a role because, surely you could do the same kind of task if you just use a classical object where you're convinced that it can't be duplicated or can't be quickly duplicated. So, imagine Bob gives Alice a copy of the handwritten diary he's been keeping for the last year, and then at some later point in the future light cone of the response point, he will ask for it back. Under normal circumstances, we would probably imagine that Alice is not going to be able to exactly duplicate Bob's diary within a few seconds. So as long as the points at which Bob is making his call are not too distant in the future, we can reasonably suppose that Alice has only one copy of the state, a copy of the diary, and then the original no-summoning theorem is going to work out in just the same way. We can still use no signaling to show that Alice can't guarantee a successful response if Bob makes calls at space-like separated points, because if she could do that, then when Bob made 2 calls, then Alice would respond at 2 points, so she would have duplicated the diary. So if we're convinced that she can't duplicate the diary, it must be impossible for her to do that. So you might then say, okay, so summoning isn't really quantum, it is really just a feature of not being able to duplicate things. Now, as a first point, it's important to keep in mind that the inability of Alice to duplicate Bob's diary is really only a pragmatic restriction. Classically, nothing forbids her from building a perfect duplication machine which instantaneously copies anything into it. We don't have such machines right now, but in principle, classical physics allows them. So that restriction on copying things is only a pragmatic one rather than a principled one. By contrast, the no cloning theorem is, of course, a really deep principle of quantum mechanics. If quantum mechanics is correct, then it is completely impossible to clone quantum states. There is no such thing as a perfect duplication machine in that regime. So that means that although in some sense you would still get no summoning results even in a classical scenario, in the quantum scenario, it's really based on the fundamental principles rather than being just based on sort of pragmatic restrictions. In addition, although it is true that the general no summoning result would in some sense apply for a classical object that can't be duplicate, the specific theorems that I've showed you today, the Hayden-May result and the generalized summoning results, would not apply to that. And that's because, as we saw in the proofs of those results, they do rely quite sensitively on the use of techniques like quantum secret sharing and teleportation. And there isn't really a classical analog of those things. Now, of course, we can do secret sharing with something like classical information, but classical information can be duplicated anyway. Whereas if you're looking at something like, a diary, which is a classical object that can't be duplicated, the same kinds of reasons that you would prevent you from being able to duplicate it would also prevent you from being able to do sort of any sensible secret sharing or teleportation with it. So in the classical case, if you're trying to complete a summoning task with an object that you can't duplicate, really your only options are going to be to just kind of send that object on a continuous path through space-time and then just respond if a call is made along that point. So in the classical case, you'd expect that the only tasks which can be completed are the ones where there is a continuous light-like or time-like path which just passes sequentially through all of the causal diamonds. Whereas we've seen for these quantum results, we don't need to have that. So we can complete tasks that wouldn't be completable in that classical sense because we have the ability to kind of delocalize our quantum information over space-time and reconstruct it later. So in that sense, the Hayden-May results and the result of Adrian and I are genuinely very quantum because they are combining these relativistic restrictions with specific quantum techniques to distribute information and then reconstruct it. You might also want to know how quantum exactly is this paradox of choice that I've set out, where giving Alice more freedom makes the task harder. And the answer is that the simple behavior of more freedom makes the task harder is not really particularly quantum in nature. So we can design a classical task which has similar features. So, for example, imagine that Alice has two agents, A0 and A1, who are located at some distance d apart. And meanwhile, Bob is also going to have two agents, one of them located near A0 and another one located near A1. So at some time in an agreed reference frame, each of Bob's agent is going to send the corresponding agent of Alice a classical bit, 0 or 1, and we'll guarantee that at least one is going to be sent. And then the requirements for Alice to complete this successfully is that they must return exactly 1, 0 and 1, 1 to the corresponding agent of Bob, and they must ensure that the 1 goes to some agent of Bob who sent a 1. Now, obviously, if Alice is assured that Bob's agents will only send 1, 1, this is completely trivial and easy to complete. But if more than 1, 1 may be sent, then there is no way for Alice to guarantee success at this task. We can see that if we can possibly have more than 1, 1, then when one of Alice's agents sees a 1, they don't know whether they should respond with a 1 or not, because if there has been a call of a 1 at the other point as well, then the other agent might respond with a 1, and then you might have 2 1s, and that would be a failure. But if you assume the other person's going to respond with a 1 and they in fact saw a 0, then you're going to end up with 2 0s, and that would be a failure as well. So if there could be more than 1, 1, there's no way to guarantee success. So again, that has this kind of feature that if only 1, 1 is sent, there's one valid way of completing the task. Whereas if more than 1, 1 is sent, there are 2 possible ways of completing the task. So again, in this case, more choice makes the task harder. And you can see that the reasons for that are kind of the same as in the summoning task. Having the guarantee of just one call gives Alice knowledge about what's going on at the other point, and that allows the agent to sort of coordinate non-locally, whereas if she doesn't have that guarantee, she's got less information to use to coordinate her agents. So indeed, the simple fact that more choice makes the task harder is not in and of itself quantum. What is interestingly quantum is the specifics of the way in which these restrictions on Alice's information interact with her ability to distribute states across spacetime. Again, the necessity proof that I gave of the theorem in the unrestricted case would still work with a classical object that can't be duplicated. But as we saw, the sufficiency proof depends on using quantum teleportation. And so that tells us that the details of which specific tasks can and can't be completed in this scenario do depend quite sensitively on quantum mechanics as well as on relativistic restrictions. So just to summarize, what we see from these tasks is that we can both gain quite a lot of interesting information about the possibilities for distributing quantum information over space-time, and we can also potentially gain some useful information about sort of practical requirements for things like distributed quantum computing. So as you can see, there are various different possible generalizations here. These are just a couple of different generalizations, but there are certainly other possibilities that could be investigated. And there are other questions we might usefully ask about the ways in which we can distribute quantum information over space-time in accordance with the constraints imposed by relativity. And what we see in this case that's particularly interesting is that we can get all of these results using quite sort of high-level, simple general constraints. We didn't have to go into any details of relativistic quantum mechanics or quantum field theory. We can already learn quite a lot in terms of sort of high-level principles just by combining these basic results from these two theories and seeing what comes out of the combination. So that is potentially an interesting route to kind of constraining our understanding of relativistic quantum information and to seeing sort of shortcuts to some of the consequences of relativistic information processing. So that is more or less everything I had to say. I guess we should see if there are any questions.
Okay, thank you very much. That was a very nice talk. Questions? The floor is open for questions.
If I may start until we have further questions. Thanks again, Emily, for the very interesting talk. So I had some questions about this, how quantum are these results, right? And indeed, you gave some quite a few interesting arguments about this, about the no-cloning theorem. Relating to that. So in particular, I guess also if we consider rather than classical deterministic states, if we consider classical unknown probability distributions, these also have like a no cloning type theorem, right? So I was wondering, on one hand, would you expect similar results in that case where you now want to teleport or summon like if there's, I mean, first of all, if there's a meaningful way to talk about summoning a classical probability distribution. And on the other hand, perhaps on the other side, one could consider theories that go beyond quantum, like, generalized probabilistic theories or so on, where as well you have sort of non-classical features and analogs of no cloning theorem. And I'm just curious if you thought about how these might fit into the picture.
Great. Yeah, I'm not aware of much work on sort of generalizing this beyond quantum states. I do think that would be a very interesting thing to do. What I can say is that for sure some kind of no summoning results are going to apply there. Certainly the basic argument in terms of these conditions being necessary does seem like it would clearly still apply because, again, if you could complete certain tasks, then you would be cloning. So you can make some of the same kinds of arguments. And those are going to be quite general across many different types of generalized theories. As long as they have a sort of effective no cloning requirement, the sort of necessity proofs are going to go through in the same way. The sufficiency proofs are where it would become more complicated because, as you sort of saw, the sufficiency proofs I gave use very specific protocols that work for quantum states and that are not guaranteed to succeed in other contexts. So to answer whether the sufficiency proofs would apply to those other theories, you would have to go and ask, is there an appropriate analog of quantum secret sharing in that context? Is there an appropriate analog of teleportation in that context? So I don't know whether anyone has looked into whether you can do an analog of secret sharing for for classical probability distributions. My intuition would be that something of that kind is possible, but I don't know if the bounds on it are going to be the same as in the quantum case. So yeah, I think that would be a very interesting thing to investigate.
Thanks. Yeah, I think I'm aware of teleportation being looked at for classical distributions and beyond quantum, but for secret sharing, that indeed would be interesting.
Yeah, I've never seen anything on secret sharing, but yeah, now I'm curious and yeah, I'm wondering now. Yeah.
Okay, thanks. And do we have any other questions from the audience? Feel free to unmute yourself and ask your question if you have any.
Okay, so maybe at this point we can stop the recording and